Okay, so I appreciate I am not in the recording studio, and this isn't typically how we do videos, but I wanted to give you a preview of this idea of stress and strain in your last content element for this unit. And so I'm going to share my screen with you. I'm going to just walk through sort of this idea of taking a material and stretching it to its breaking point and its limit. So what appears as though we're not necessarily moving the material, applying a force and causing it to translate motion, but we're stretching that material like steel or bone or wood and getting it to its breaking point. And so what does that look like and why is it important? You can imagine a lot of applications for it. Let's just a very brief introduction to this idea of stress and strain. Okay, so imagine that we have, let's say this is a steel pipe and it's attached here to one end. If we apply a force to one end of the steel pipe, pulling on this force, we're going to get some small changes in the pipe's length. And as we look at the force, as we change the length, as we increase force, we increase that change in length, and that has this linear region associated with that increase. And this is no different than when we looked at Hooke's law, right? So if we looked at a spring, an elastic material, remember that as we applied a force, the force was equal to the spring constant times the change in that object's position, the change from the rest position. Well, that's just the change in length if we think about this moving from its rest position. So this part is simply just this idea of Hooke's law that you've already looked at. And then there's this nonlinear region up to the breaking point of the object. So how a material stretches depends, of course, on the spring constant properties of the material. Well, then we'd have to know the properties of all the materials to see how things worked from a breakpoint perspective. Well, if we look at it from a molecular perspective, however, we can actually look at the proportions of the forces at a molecular level to that change in length. So what do I mean by that? Imagine that this pipe, of course, has some dimension. And when I apply a force to the end, I'm kind of applying a force across this entire area of the piece of steel from a molecular perspective, this whole area, and I'm pulling these molecular bonds apart. And that force per the area at which I am pulling on, the area of the pipe, is related to, proportional to, how much that length changes by molecularly relative to the length of the pipe itself. Okay? Now, this proportionality has a proportionality constant related to the type of material that we're dealing with in a way similar to K having that property. But remember, K is going to depend on a whole bunch of different things. So this proportionality constant is what is known as Young's modulus for a given material. We use the variable Y. And it's called Young's modulus. And so this is for a given material, and it describes, in an essence, how much force has to be applied to that particular object, dependent on its area, that particular material, to get the object to change its length, to stretch that steel pipe just a little bit. So let's use an example on how we might utilize this idea. I want you to imagine that you have a 2-meter long wire suspended from the ceiling. Okay, so here's my 2-meter long wire suspended from the ceiling. And this wire has a diameter of 1 millimeter. I'm going to look at my notes on my lap here. So a 1 millimeter diameter wire. Now, I go and I take a mass, and we'll just say that this mass is 4.5 kilograms, and I hang it on this wire. Now, we know at the molecular level that this wire is stretching just a little bit as we hang that wire. And as we hang that mass, if I hung a heavier mass, it stretched a little bit more. If I hung a heavier mass, it stretched a little bit more. And eventually it might get to that breaking point where the wire itself cannot withstand the mass that's hanging on it. So how much do we change the length of this wire when we hang this mass on? Well, let's say we stretch the wire by 1 millimeter. I saw 2 millimeters in my example and I started to think I was looking at the wrong thing. So we stretch the wire by 1 millimeter with the mass hanging. What is Young's modulus for this material? All right, well, we want to first think about what is the force acting on this material. What is the force acting on the wire? Well, it's the hanging mass. So we know that the force acting on the wire is equal to the mass times G. So 4.5 times 9.8. So the mass, the force acting on that wire is 44.1 newtons. All right, so we know that the force acting along that area, that's going to be the cross-sectional area of our wire, is equal to Young's modulus times the change in length as a proportion of the length of the wire. So we have 44.1 newtons. Our area, this is a diameter of 1.0 millimeters. So that's 0.001 meters, which means we have a radius of 0.0005 meters. So pi times the radius, 0.0005 squared, is going to equal Young's modulus. We said our change in length is 1 millimeter, excuse me. So it's 0.001 over my 2 meter long object. So we have our force per area is equal to Young's modulus times the change in the length as a ratio of the length. So 44.1 divided by pi times 0.0005 squared times 2 divided by 0.001, and we get 1.1 times 10 to the 11th newtons per meter squared is equal to our Young's modulus. All right, so that's standard for a given material. And in this case, that material with around 1.1 times 10 to the 11th newtons per meter squared is likely to be copper. Okay, so just utilizing that equation. Now, those of you who are going to need to use stress and strain as you go on in our construction majors, for example, or engineering majors in the course, as you go on in your coursework, you'll get a little bit more into this. There's also a volume modulus called the bulk modulus. We are just going to do a quick introduction in this semester and this last sort of content for the year. But I do want to give you a couple more pieces of vocabulary relating to this relationship. The ratio of the force per area is what we know as the tensile stress on an object. So it really is the force, the stress we're putting on that object. That force per area also goes by the term tensile stress. And this ratio of the change in length per the length is what we refer to as the strain. So this is when we're talking about sort of the idea of stress and how much strain we're putting on that object. The stress really relates to the force per area that we're applying to that cable, that bar, that piece of wood. And the strain is what we refer to as the change in length per length. Okay, so example of how we apply Young's modulus, pretty basic introduction to this concept, and we should be set to explore that introductory in your practice problems. All right, good job.